Welcome to Breadboarding. This is video 18 in the Breadboard 8088 PC series, and in this video it's part 6 of building out a monochrome display adapter. Now the video controller we're building is an important part of building the basic floppy disk PC. You can see the steps leading down to being able to boot MS-DOS from a floppy disk. And then the next stage would be add a disk controller and other components and eventually try and run an early version of Windows. Now in the last video we tested the video digital analog converter and the CRTC, and we were able to get black, white and grey output, the monochrome settings, also for green, which is probably closer to the original phosphor monitors that the monochrome display adapter originally used. And then also we added support for CGA colours. A little known fact was that there were some versions of the MDA adapter with an appropriate monitor you could actually output colour to. However, IBM only released a colour monitor in about 1983, 18 months after the MDA adapter was originally released with the first PC. So in this video we're going to be looking at adding the character latch, the character generator EEPROM and the shift register, which is necessary to serialise the raster image of the characters, and then we're going to test the character output. Now, if we look at the block diagram, then last time we added the CRTC video RAM and the digital analog converter. And in this video, we're going to be adding the character generator on. This will have a VGA 8x16 font, 16 rows, 8 bits across. And this is driven by the raster address or row address coming out of the CRTC. So the first 4 address lines of the character generator ROM are from the RA0 to RA3, going to A0 to A3, and then the video RAM, in fact, outputs 1 byte to choose which character, and though character values 0 to 255, 0 to FF actually then go to the A4 to A11 lines. So then we need to add a latch for the character output because the video RAM is going to be switching between the attribute output or color output and the characters. We need to latch the value. So in fact the value is going into the character generator ROM here for A4 to A11 in fact will be latched. And then the data output from the character generator ROM is the raster image of the character, and that goes into the shift register, and then the dot clock then rotates the various bits in that out to the video DAC. And for the moment all we're going to be doing is using 2 colours in the video DAC, probably black and white or grey, and the foreground back just chooses between 1 and 0 if we're using foreground or background. The shift register is latched using the shift register latch signal. The clock for the shift register comes from the 25 MHz dot clock. So let's take a look at the fonts that we're going to use for this. So in the previous Nanocomp 6809 project, we've already developed a VGA compatible video controller, and as part of that, we made use of contraption and the information on the int10h.org. So int10h I think is interrupt 10. We're going to be using a VGA font which is 8 bits wide and 16 rows high. The original MDA fonts were 9 bits wide and 14 high. However, the actual characters were in the ROM were only 8 bits wide, and there was a circuitry to extend the last bit under certain circumstances, which you talked about when we went through the schematic diagrams. Now, the NDA fonts used to use underline for the row address 12 or 0C, and you can see here that where the underline would go is actually on this row, so it's level with the lower descender of the lowercase y. And then if we look at the VGA 8 one, then C is actually obviously a little bit too high. So in fact, we need to drop the underline down to E, which is 14, row 14. So you can download Wrapped or Fronttraption from the int10h.org site. It's a great site, lots of useful articles, all sorts of background information on CGA and all sorts of other things, in particularly the way how you can get composite output from CGA to get many hundreds or even 1,000 colours out of the composite video modes. So recommend you take a look at here, and you can also download the fonts from here as well. And what we're going to be doing is taking the VGA 8 16 row font, and we're going to be burning that into an 8K EEPROM. So let's take a look at the schematic diagram in KiCad. So this is where we left it last time, and what we're going to be doing in this video we're going to be adding the character latch, character generator, EEPROM, and the shift register. And what we'll be able to see if we go into a little bit, zoom in a little bit. So the character latch is driven by the output from the dual port video RAM. So the video side of this is going to be going to the character latch there, and you can also see it goes to the attribute latch that we'll be doing in later videos. Then the output of the character latch, and that goes up to A4 to A11. So you'll see that the lines there from CH0 to CH7 go from A4 to A11. A12 is just tied to ground because we're only using 4K of this 8K chip. And then the lower A0 to A3, those are tied to the raster address or row address from the CRTC. And you can see down here the CRTC is outputting that, and that just tells the EEPROM which row of the caret we need to be showing at this particular point in time. So that'll go from 0 to 15. It's also used to drive the clock PLD here, in that the clock PLD produces a signal when the underline row is selected. So under the VGA fonts, when we've got row 14 or 0E, then we'll get a signal coming out on the underline. So let's just have a quick look at the board as we left it. So there's quite a few fly leads and things. In another video or two time, once we've added most of the chips, I'll tidy this up and we'll get rid of some of these fly leads and things, and I'll route them cleanly, but there's not much point in doing it at the moment because things are going to have to change anyway. So we're going to be adding the character latch down here, and it's going to have output from here coming to this side. Then outputs from there are going to go to the character generator EEPROM, will be up here. So we're going to need to move this inverter, probably just move it over here for now. And then the shift register is going to go in here. And the output from that shift register, we're just going to use to drive one of the P0 to P4 inputs onto the video DAC. What that should allow us to do is to be able to output the characters. What I might do to start with, similar to what we did in the previous video, where we actually tied the video DAC to some of the CRTC address lines, we'll probably tie the address lines here to the ROM here to start with before we actually wire in the character latch here. And all that will do is allow us to check to see whether the shift register and the character generator ROM are hooked in properly, and that'll just generate sort of 256 characters across the screen as a CRTC goes through the address lines. And then once we add the links from the character latch into there, we should be able to update the programs then to be able to set the video RAM to the contents and do some sort of test patterns and things. Just need to tidy up the board, take out those test lead, the inverter, display enable, and the horizontal sync, fit the new chips, and we just need to move the character latch down a bit to give space. So first thing we need to do is to program the EEPROM with the appropriate data. So selected the AT28C64, so this is an 8K. I'm just going to read it first. We've got something in there. Now we're just going to load the font. So I've copied the font from the download. So it's VGA8, so it's 8 bits wide, F16. That means it's 16 rows. Okay, so then we can see the first characters, in fact, all zeros. So now we're going to program that. Okay, so that's programmed. Okay, so just need to put the EEPROM in here. It goes with pin 1 at the top of the board. Probably need more holes on the right hand side than the left. You can always guarantee whichever way you do it, you'll probably find it's the wrong way. And we need to leave a bit of space for the wires to come down to here. Okay, so let's give that a go. Okay, so I'm going to check these off the diagram and wire this up, and I'll speed it up, and when we come back, hopefully this will be wired up and ready to start doing some testing. Okay, so just going to wire in the power connectors to make a better physical connection between the new board and the existing computer. Then we're going to add the memory read to the top of the board up there because we missed that out. Now we need to put in the address 0 for the video RAM to QB, the display enable up to blank into the video DAC. Now we're going to wire up the various connections to the shift register. So the dot clock goes in first, then we're going to tie the ground and various other pins to ground and to 5 volts. Reset. Now I need the shift latch clock, and then the output of the shift register goes to P0 on the DAC. Now these are the data outputs from the EEPROM. We just need to label these so we can track them. Now when I wired these up, unfortunately I paused the video after I'd done the first of the red lines, so they just appear magically. And I also then wired in the outputs from the CRTC to the address lines as well, but the video is paused. So just put in the tie to ground for the output enable, chip enable. Okay, so finished wiring that up. I just was checking against the schematic diagram and I realised there were a few things I'd missed. So there was one ground tie here for the clock inhibit, and if this is not tied to ground then the shift register won't do anything. So I'm just going to plug that in there. And then also, although we've got one input into the digital analog converter, we really need to tie a lot of those inputs to ground. So I'm just going to put in a couple of ties to ground and then we will jumper the rest of the pins together. Okay, so I think we've got the P0 is tied to the output of the shift register over here. That should have the rasterized character, and then all the other ones are tied to ground for the moment. So that should mean we're only going to be using the 0 and 1 palette entry. So just going to plug in the serial cable, plugged in the video capture, VGA capture card. So we just need to now download a test program. So to start with, I'm just going to download the black and white test 1, so MDA test 1. Okay, so powered on the nanocomp, we're just going to send the first test program down, which will just do probably grey and black. So I've put the nanocomp into load, send file, so that's downloaded, and then when we start this, we'll just go to the screen share. So don't have any output at the moment, and then when I run the program it should initialize the CRTC and should then give us a nice repeating pattern of the VGA character set. So you can see here that the first character is actually a blank, then we've got a smiley face, so this is a good start. This is, I think, this will be a light grey, not white, because of the palette that we were using. So that's indicating that things seem to be working okay. But what I'm going to do now is, now we know that the character generator is working and the shift register is working, we can now wire up the input to the character generator to come from the video RAM and the character latch, and then that should allow us to set whatever we want as a test pattern on the display. Okay, so now we're going to connect up the character latch with the video RAM. So we can see here I've labelled all of these, so when we click on each of these, hopefully we should see, there you go, so you can see that the output of the left hand side of the dual port video RAM, so this is the CRTC side, is going to the character latch and the attribute latch. We'll be wiring the attribute latch up in later videos. And so just for the moment we need to wire in the video data 0 to 7 over to here, and then we need to wire in the character latch clock signal into the clock, and then the output of character latch is then going to go into the input to the character generator ROM. So we're just going to remove our test leads out of there and we can just move them over to this side over here. So we're now going to wire in the pins from here to here and from here over to here, and we're just going to use this cable for the moment. Okay, just going to wire in the power for the character latch. Then we're going to need to take the character latch signal from the clock on the left hand side over to the clock signal. Then we're going to wire in the output of the character latch to the address pins of the EEPROM and then the data. Then finally we need to wire the output enable to ground. Okay, so we're ready to try it now with the video RAM hooked up to the character latch and the output there. Now to start with, when we do this, we're just going to get random characters on the screen because we're not setting anything in the test program in the video RAM. So I have put in the decoupling capacitors. I'd forgotten to put decoupling capacitors in on the board, so I've actually put 0.1 microfarad decoupling capacitors close to the ground rails of most or all of the chips. So that's to prevent ground bounce. What I'm going to do now is to turn it on. So let's just see if it comes up. 4.84 volts, that's okay there. And we're going to download the test program again. Send the test program, get ready to run it. And if we go on to the VGA capture, okay, so when this program runs, it should initialize the CRTC and we should see random characters appear on the screen. Okay, so we're getting random characters, but there's a bit of interference there. Something's not quite right. When I put my finger over a bit of the board, it sort of seems to sometimes fix it. And in fact, what I realized when I had a little test of this earlier is that there's one of the output enable signals on the video RAM that I hadn't actually wired to ground. By wiring this to ground, which I'm just doing now, and then we get a stable picture. So that seems to be working okay. So all we need to do now is to update the test program to actually initialize the video RAM, clear the video RAM and put some sort of test pattern on. So I'm going to take one of the test programs I used from the 6809 series and I'm going to upgrade that to run on 8088, 8086, and then we'll see whether or not we can get that coming out okay. What we're probably going to need to do is to adjust the display enable signals, because at the moment there's no delays on those, and we know that CRTC is capable of delaying the cursor and the display enable by 1 to 2 clock cycles, and I suspect that we'll need to do that once we actually get a test pattern up there. Seems to be working, and we just now need to write the software. So if we have a look at the test program, so this is based on one of the CRT test programs I had previously in the previous series, and a lot of this is what we looked at last time. So we've got our CRTC initialization, the palette initialization. Now we've got a clear screen. We output some characters along the top line, sort of from 1 to 0 repeated across the screen. Then the 10s below that. Then we do the same thing at the bottom of the screen. Then we do the line number from 2 down to I think 24 down the left and right hand side, and then we dump out the characters. So this is basically the similar to what we had before, and I've just done a very rough and ready conversion. And then there's the print number, print digit and print hex are some of the helper routines which are also being converted. So if we just assemble this, so now we need to send the file down to the nanocomp, so just make sure we've got number 4, yep. So load, send file. Now if we switch back to the VGA capture, now when we run this we should have the test pattern up here. And great, so we've got a pretty reasonable test pattern. You can see that starts at 1, the 0 at the end, which will be 80, is just missing a little bit. We can see that we've got 25 rows, and we've also got the character set being dumped out there as well, which all looks pretty reasonable. The only issue here really is I've also tweaked 1 or 2 of the settings to get the display to fit better. So what I've done is change the horizontal sync position from 53 to 54, so it just meant we got an extra character on the end there. And I've also made use of the display enable skew by 1 character, so that's 1 in the interlace mode is actually giving us 1 character delay to the display enable. And what I also found was that, as I suspected, I actually needed to change the CRTC clock to actually work off the inverted character clock rather than the standard character clock. So I've actually modified the connection on the PLD to feed the CRTC from the inverted character clock. So we've been able to install the character latch, character generator, EEPROM, and program it, and the shift register. We've done quite a bit of testing there, and we've also now got a nice display pattern. So in the next video, what we're going to do is to start adding the status register, control register, and the blink clock PLD, and that will be needed so we can then add the attribute latch, the attribute multiplexer, and the video output PLD. And the video output PLDs are the thing that encodes most of the complex rules to do with flashing, blinking, reverse video, and underlines. If If you don't want to miss out on future videos, please hit subscribe, and if you found the content useful and interesting, please hit like. It just helps to make it available to a wide number of people. Thanks for watching.